investigate the science behind space weather. And so today I'm going to take you from where space weather starts, the sun, where all activity in our solar system starts, out into the solar wind and see the effects of the sun on the magnetosphere of Earth, and those effects on the upper atmosphere and ionosphere of Earth, and on Mars, and then extrapolate to exoplanets. So we'll start from, maybe I push this way? Oh, sorry. My first hyperwall talk. Okay, so start from the sun, and here we have image from the Solar Dynamics Observatory in a visible wavelength, in the optical wavelength, and we can see the photosphere here, and you see activities. Oh, I'm not sure. Is there a pointer? No. Okay. You can see the activity here with the granules in the sun and the sunspots, and this is called where the sunspots are, the active region. And this is the image that we see in the visible wavelength. But with the Solar Dynamic Observatory, it's coming. Okay. Solar Dynamics Observatory actually sees in a lot of different wavelengths, and the reason we do that is because we can see different types of activities on the sun with those different wavelengths. You have the some in ultraviolet and some in X-ray and in visible. And what you can see is like when you have with the sunspots that appear just dark in the visible, in the UV have ribbons of activity you see the magnetic fields coming out of the sun. And filaments that show up at certain wavelengths are dark in others. And if you can see, once this stops, you can see that the edges at the edge of the sun here we go. As you can see, at the different wavelengths, the edges appear at different altitudes, at different radiuses, basically. And that's because we're imaging different activity along the sun. And then here's a good picture of where you have an active region there and activity, and you can see the magnetic fields in and out of the sunspot region and activity that way. So I also want to encourage anybody who has questions to ask them as we go along. It makes it much more interesting for all of us. So, any questions? All right. So the sun not only sends out UV radiation, or radiation out into the solar system, but it also sends out. It has explosions off the sun. This is a picture from Solar Dynamics Observatory, again, a movie where we see an active region exploding for the coronal mass ejection. This was a M-class flare that sent out a massive coronal mass ejection that exploded off the sun and sent particles streaming towards Earth and the solar system. And what you can see is that when the explosion happens, the material that's moving away from the sun is actually darker, and that's why it appears darker against the. It's actually cooler, excuse me, and that's why it appears darker against the brighter solar disk. And then this material adds to the constant stream of. Yes, Alan. Well, thank you for the question. Actually, we do. We have coronagraphs out in space, or a coronagraph out in space. The SOHO mission from ESA and NASA observes coronal mass ejections and able to get properties off these coronal mass ejections such that our space weather prediction centers, like the one we have in Boulder and across the world as well, can predict how long it will take that coronal mass ejection to get to Earth. And then when it gets near Earth, we have another spacecraft, the Advanced Composition Experiment Explorer, that's 1 million miles away from Earth. That's kind of an upstream buoy, so we can get the space weather parameters of the cloud of magnetic gas coming towards us, and that'll tell us, as I'll show a little later, what the effect, what gives an idea of what the effects are going to be in the near Earth space. So the effects on our magnetosphere and our ionosphere, and on possibly our technological infrastructure. And so as I said, the sun spews out a constant stream of particles, the solar wind. And then this is an image, this is a movie taken of Comet Encke in 2007 from the Stereo spacecraft. And this still gives me chills. I remember watching this at AGU in a dark room in a session, and the whole room was quiet. And then you hear this gasp when the comet comes up, and you see the tail flapping around in the solar wind. And this was actually the fact that comets have a tail was actually the inspiration for Parker. The scientist who postulated the existence of a supersonic solar wind. And you hear all about the Parker Solar Probe, which is going to visit the sun and investigate how the solar wind is accelerated in the next talk that Nikki's going to give. So looking at comets' tails inspired and gave us an understanding of that there is actually a flow from the sun, and that's where this the beginning of kind of our understanding of the near Earth environment in that sense. To wait. And so this is a movie that starts from the sun and coronal mass ejection, and this is again using based on Solar Dynamic Observatory images in the ultraviolet, where we see these loops of magnetic fields, and these particles stream out from the sun and head out into the solar system, and the different colors denote the density of the stream from the sun. And so you have in this case, the solar wind streaming out, coronal mass ejection that's streaming towards the planets, and it'll eventually here it's going to hit Venus, and Venus does not have a magnetosphere to protect it against the solar wind, and so it hits directly into the Venus atmosphere. But Earth does have a magnetosphere, and so it deflects the particles around Earth, deflects the solar wind particles around the Earth, and protects it in that sense. But the energy and the mass, and then the particles from the solar wind do perturb the magnetosphere of the Earth, the magnetic field around the Earth, and that causes us space weather effects in near Earth space here. So here we see the magnetosphere here. This is the magnetic field. It's here going this way, south to north. And so here's a simulation created by the Coordinated Community Modeling Center at Goddard that shows the effects of the solar wind on the magnetosphere. And so these lines here of the incoming solar wind, here's the lines of the magnetosphere here. The color denotes density, red meaning high density, blue meaning low density. And when you have an active solar wind, you have what happens here. You can see the magnetic field lines compressed in. First, what happens is reconnection, where the lines of the solar wind connect with the Earth's magnetosphere and impart energy into the system, and that's called reconnection. And that compresses the magnetosphere and causes disturbances in near-Earth space. So here's another simulation of a much more active time, where basically the whole magnetosphere is compressed in and essentially stripped down into the Earth. And so when that happens, you can think of for instance, our geostationary satellites, which are flying out here, are exposed directly to the solar wind. So one manifestation of kind of this interaction between the solar wind, the magnetosphere, and our upper atmosphere is is the Aurora, and what you saw there was the Aurora Australis taken images, a movie taken from the International Space Station in 2011. And then once the Aurora moves off the screen, what you see here is the day glow and night glow that that in the upper atmosphere, the green line, and you can see it up here, the red line and red Aurora there, and those are just as we use different wavelengths of light to image the sun, we use different wavelengths of light to image the upper atmosphere as well and gain physical information about the upper atmosphere. So why we care about these effects in space weather is shown in this kind of movie here, where we have effects on near-Earth space. And even in low Earth orbit, satellites can get spacecraft charging, can have particle radiation that upsets their circuitry and commanding. There's been a couple of cases where we suspect space weather was the cause of satellite deaths, basically. And in addition, our technological infrastructure is we are so dependent on that now on GPS. These sort of geomagnetic disturbances affect navigation and communication, as well as a high frequency communication and navigation, as well as they can possibly cause effects on the ground, where a large geomagnetic storm can actually disrupt our power grid and bring it down for certain amounts of time. So one thing what's upcoming in NASA, the next heliophysics mission to launch the next two heliophysics missions that are going to launch are the GOLD mission, which is a ultraviolet imaging spectrograph on a geostationary satellite, and the ICON mission, which is a low Earth orbiting spacecraft looking at magnetosphere ionospheric effects at low latitudes and looking at the dynamics of low latitudes. And GOLD is going to image the disk, the Western Hemisphere, across in the north and across in the south like that. And it's going to be our first upper atmosphere weather satellite. So it's going to revolutionize what we see in the upper atmosphere, just as weather satellites have revolutionized what we see in terrestrial weather. And at the same time, ICON is going to be looking at the particular mechanisms in the low latitude ionosphere that generate some of these irregularities and some of these phenomena that affect our communications and navigation. So quickly, I got 30 seconds. Solar wind, also, the space weather effects are also happening on other planets. For instance, what we're learning from Mars is that the solar wind, because Mars lost its magnetic field millions of years ago, or billions of years ago, excuse me, we now understand that that's what stripped Mars of its atmosphere, because we know from geological records that Mars once had running water on the ground, and that required a large, high-density atmosphere. But because the magnetic field was stopped, the magnetic dynamo stopped for some reason a few million years ago, the solar wind actually stripped the atmosphere of Mars there. And that's what we learned from the MAVEN spacecraft that went to Mars just recently. And the last slide I have is talking about how we extrapolate what we've learned from Earth and Mars into defining the habitable zone of exoplanets. So at one time, we defined habitable zone basically just on the distance away from the star. So an exostar, given the amount of radiation it has, we would define habitable zone depending on how whether it was the right temperature for water to happen at the planet. But now we know if we factor in space weather, we can define that much more finely, depending on the conditions of stellar activity and also being able to seed the chemicals that we believe are the building blocks of life. So thank you. Any questions?